So indicators are substances that we add to solution and that change color depending on the conditions. What we're mainly talking about during this topic are acid-base indicators. And so these are going to be molecules, usually organic molecules, that will change color depending on the pH environment that they are in. Now, most of the time, we are going to think of indicators as actually being weak acids that exist at an equilibrium. So here's the weak acid molecule on the left, represented by H-IN. That stands for indicator. And on the other side, the indicator has donated a proton to the water, acting as an acid. And on the other side is its conjugate base, which is represented by IN minus. So this is the conjugate base ion that's left over. So we think of indicators as essentially existing at this equilibrium where there are two different forms of the indicator present. And based on additions of H plus ions or OH minus ions, this equilibrium will shift, and we will either have the majority of the indicator in this form, in its sort of molecule form, and then we will see the color, what we'll call color A. And if we cause the shift to the other side, then we'll get color B. That's the idea. Now, a more detailed picture is that this actually has to do with what's called the conjugation in the molecular structure of the indicator. Conjugation is when there are a series of alternating double and single bonds, which allows a big section of the molecule to have delocalized pi electrons in it. And that's actually part of the reason why those molecules end up having color. When you have all these delocalized electrons, then they can absorb energy in the visible spectrum. And so you end up observing the complementary color. That's not part of the acid-base topic, but it might be part of an option that you cover later on in the course. I just thought some people might want to know that. Anyways, the indicator topic is generally pretty simple. It's a pretty easy portion of the acid-base topic. When you add acid, you should think about this as adding H plus or H3O plus. And if you look at the equilibrium up here, you should know that if you add a stress to the right-hand side, it's going to shift to consume that stress and lower that stress. And that means that when we add a lot of acid, we're going to end up producing mostly HIN in the solution. The IN minus will get used up as we shift left. And so primarily, we're going to have this form of the indicator in the solution. And so we're going to get color A. So we're going to shift to the left to consume extra H plus. That removes the IN minus form of the indicator and produces more HIN form of the indicator. And so we end up seeing color A. I'll move that over here. Okay, so mainly we're going to see color A. So color A represents the acid color. You can probably guess that color B represents the base color. If we add base to the mixture, you might notice there is no OH minus in this equilibrium because we're thinking of it as a weak acid. But we should know that one of the classic reactions is that H plus reacts with OH minus. That is neutralization. That is the net ionic equation of neutralization. So when we add OH minus, what it net does is it converts to water, and so we essentially end up removing H plus from this equilibrium system. So you can think of it two ways. Either by adding OH minus, I've removed H3O plus from the system, which would cause a shift to the right to replace it, or adding OH minus produces more water. Water is on the left-hand side of this equilibrium, and so therefore it will shift right to remove it. Either way, adding OH minus leads to a shift to the right, which means the amount of HIN is going to go down, and the amount of IN minus is going to go up, and so we're going to observe color B. So when we add base, we're going to shift right to replace the lost H plus / to remove added water. And we're going to get color B as IN minus will have higher concentration and HIN minus will be consumed. Okay, I'm going to move that so we can see it more clearly. Let's see. Maybe I need to go down. Give it a little more space. Okay, sorry about that. So that should be pretty simple equilibrium 101 type concepts. There are some indicators that you should know a little bit about their colors, and then there are some that you can find in the data booklet. So litmus is sort of a classic pH indicator. It comes from a natural substance, and then we have litmus paper, which can test for things being acidic or basic. And so the acid color of litmus is red, and the alkaline color is blue. Universal indicator is another indicator you should know a little bit about. It transitions through a variety of colors because actually it's a mixture of indicators. But again, the classic acid color is red. Classic basic color is a dark blue or a kind of a purple. And it fades through orange, yellow, green, and then kind of teal into blue as we go through the pH scale. Other acid-base indicators are listed in section 22 of the data booklet. And there are a couple of key bits of information that they give you. It's pretty easy to interpret, but you should make sure you know how to use this. So the pKa is giving you information about just how acidic or basic the indicator is. But really what's important about it is that the pKa is this number is actually the pH value around which the indicator changes color. So methyl orange is an indicator which will change color around pH 3.7. Methyl green is an indicator that will change color around pH 5.1. Phenolphthalein changes pH around 9.6. Okay. Now, actually, the color changes across a range of colors, and so what that means is that for example, bromothymol blue doesn't just change immediately at 7. It's going to be changing color between pH 6 and 7.6. And since its two colors are yellow and blue, in between, during this pH range, it's probably going to appear kind of greenish, right? Methyl red in this pH range will appear kind of orangish because that's between red and yellow is orange. So pKa is the precise pH around which it changes, and the pH range is where it's actually sort of in that transition. And these are the colors that it transitions between. So at a pH that is more, it says this is the acid color, right? So at a pH below this value, that's where it's going to appear red. So if you use methyl orange below 3.7 pH, so like at 3 pH, it will appear red. But if it's pH 5, then it's going to appear yellow. So on either side of that pKa value is where you're going to see distinctly these colors. And in this pH range part, that's where you're going to see the color transitioning between them. Okay, so acid color is more acidic than the pKa pH. Alkali color is more basic than the pKa pH. Okay? And actually, the pKa value is where, when the pKa equals the pH, that's actually where the two indicator forms are equal concentration to one another, which is why the color is transitioning at that point. If you're at a much lower pH, then you mostly get the HIN form, and so you just see that color. And if you're at a higher pH, you mostly get the IN minus form, you see that color. But right when the pH equals the pKa, that value is very special because it's where the two concentrations are equal. And so you sort of see both colors, and that's why you see a transition color. So you should know how to use this table. It will come up on the HL syllabus about picking appropriate indicators and being able to figure out what colors they would be at different pH values.